Hello and welcome to ENGR 330 Fluid Mechanics Recitation on Chapter 5. So let's look at problem 5.3 from your book. Water flows steadily through the horizontal piping system shown here. The velocity is uniform at section 1. The mass flow rate is 10 slugs per second at section 2 and the velocity is non-uniform at section 3. In part A, you're asked to determine the value of quantity, which is this material derivative for the system, rho dV. You can immediately see that the intensive property here, the quantity for B is 1. Okay, so that means we are talking about mass conservation. Okay, you can quickly tell that from there, where the system is water contained in this pipe is bounded by these three sections. And in part B, you're asked to determine the mean velocity at section 2. And part C, determine if possible the value of this integral over the section 3. If it is not possible, explain what additional information is needed to do so. Okay? In doing these problems, first it would be ideal to set up your control volume based on what you're asked to find. Okay, so I can probably set up a control volume here which is coincident with our device. Okay, so this would be your control volume. Okay, so once we have that, if we look at the contents of this control volume, this says that is there any change with respect to time for the mass. Okay, so immediately from the conservation of mass, you can say that integral rho dV for the system does not change. Therefore, d over dt of the system using the mass conservation principle is 0. Okay. Okay. Now let's look at part B. Okay. So you're asked to find the mean velocity at this section 2. Okay, let me have this figure on this side, or I can show you when it is required. So you can see that you can find m dot of 2, which is nothing but the you can come up with your mass flow rate because which you are given. Okay, so m dot 2 is nothing but the density of water, cross sectional area at section 2, and some average velocity at B at section 2. Okay, so you can determine that, you know rho, you know A2, you can determine B2 average, you know m dot. Okay, so if you do that, if you can find the density from the tables for water in British units, you'll determine B2 average to be 17.2 feet per second. Okay, so in the third part, this is part B. In part C, you're asked to determine this quantity here, and you can see that this is nothing but m dot 3, or the mass flow rate going out of the section 3. So from the conservation of mass principle, if you, the way you set up the control volume here, whatever is coming in should be equal to the sum of whatever is going out at section 2 and section 3. So that would mean m dot 1 should be equal to m dot 2 plus m dot 3. Okay, so I can determine m dot 3 as m dot 1 minus m dot 2. Okay, I already know what m dot 2 is. That's given in the problem as 10 slugs per second. Okay, I have to find m dot 1. I know a velocity, I know the cross-sectional area, I know the density of water. Since that's the fluid, I can quickly find that. So that would be rho A1 V1 minus 10 slugs per second. So if you put in the numbers here, you should determine m dot 3, or this quantity here would be 10.4 slugs per second. Okay, so this is how you solve this particular problem. Now let's look at another problem. This is a famous problem when you get into higher classes in fluid mechanics. For now, we are looking at an idealized problem where we are asked to find a specific quantity here. So flow of a viscous fluid over a flat plate surface results in the development of a region of reduced velocity adjacent to the wetted surface as depicted. So the velocity gradually increases to the free stream to u, but it is 0 here and it gradually increases. This region of reduced flow is called the boundary layer, this guy here. At the leading edge of the plate, the velocity profile may be considered uniformly distributed with a value of u, which is what we have here. All along the outer edge of the boundary layer, the fluid velocity component parallel to the plate surface is also u. Okay? And if the x direction velocity profile at this section 2 is given by this profile, we're asked to develop an expression for the volume flow rate through the edge of the boundary layer from the leading edge to a location downstream at x where the boundary layer thickness is some delta. Okay, so let's define a control volume here. Okay, since we are interested in what's going out here or what's coming in, let's engulf this region as your control volume. Okay, so that's your CV. Okay, so we want to find what's coming in here and what's going out. Okay, let's represent what's going out here is m dot 2 mass flow rate at section 2 and the mass flow rate in section 1 as m dot BL or boundary layer. Okay, so again we can apply the conservation of mass principle for this control volume. We can see that whatever is m dot BL should be equal to whatever is going out of the control volume, which is m dot 2. Okay, so m dot BL will be equal to m dot 2, and we can write this as A2 rho V dot N dA. Okay, and we are given it's an incompressible flow. Okay, so that means density is a constant, and also m dot BL is nothing but rho A V BL. Okay, ABL, and ABL VBL is nothing but the volumetric flow rate or Q. Okay, so I'll write that. So it was rho Q BL. Okay, so let me write it on another piece of paper here. So rho QBL is equal to integral a2 b dot n dA. Okay, and if you look at this control volume here, the unit normal is going out of the surface, and so your velocity profile and n are in the same direction, so v dot n will be a positive. Okay, and you are given the relation of the profile, so I can write this as QBL. I can take out the densities, I can cancel them, okay, since it's incompressible. Q dot QBL and the boundary layer is nothing but U times Y over delta, okay, 1 over 7 dA. Okay, and you can see from the figure, right, if this is your x direction and this is your y direction, right, this is x, this is y, the area here for this section, right, will be y over delta times some L, which is the width of your plate. Okay, it's not given in the problem, but we can assume a variable here which is L. Okay, so L is the width of the plate. Okay, so if I do that, I get QBL integral A2, U is a constant, so I'm going to take it out, Y over delta 1 over 7, and for now I'll keep y over delta here, whereas L is a constant, so I'm gonna put it outside. Okay, the reason I put it here is you can see that the integration variable here to be the same. Okay, so I can write this as LU. Now I have to determine LBQ. What would be the limits? Okay, we have written it only as one variable, so our limits of integration would be 0 or some y. Okay, and we can determine these definite integrals from the figure. You can see that at y equal to 0, y over delta is 0. At y equals delta, y over delta is 1 because y equals delta, right? So I can write this as integral 0 to 1 y over delta 1 power 7 d of y over delta. Now we can quickly integrate this. This is L u, okay, y over delta 1 over 7 plus 1, 1 over 7 plus 1, and the definite integral going from 0 to 1. So if you simplify this, you'll end up with 7 over 8 u L delta, which is the mass flow rate or the volumetric flow rate through the edge of the boundary layer as was asked in the problem. Okay, let's look at another problem. We started doing this problem in class, but still it's a good problem, so let's look at it again. Water flows through a horizontal bend and discharges into the atmosphere as shown in this figure. When the pressure gauge reads 10 psi, the resultant x direction anchoring force Fax and the horizontal plane required to hold the bend in place is shown in the figure, okay, which is this guy. You're asked to determine the flow rate through the bend, okay, which is q dot, which would be the same here, and also the y direction anchoring force Fay required to hold the bend in place. So the flow is given that it is not frictionless. So immediately that should tell you that this is not an ideal case for a Bernoulli type of application. So you cannot really use Bernoulli equation here. Okay. So for this problem, first it would be ideal if we can represent a control volume. So I can pick a control volume like this. Okay. So if I do that, so if I represent this as my control volume, I have these forces here, and this pressure can also be converted to a force based on the area we are given. Okay, so all we have to do here is try to apply the either the linear momentum conservation principle in the x or in the y, depending on what we are asked to find. Since in the first case, since we are asked to find the flow rate through the bend, let's try to apply, and if I say this is my x, positive x, this is my positive y, let's apply the linear conservation momentum equation, okay, in the x direction. Okay. If I do that, for this section here, let's say this is section 1 and this is section 2. For section 1, your velocity is going in this direction, in the positive x, whereas your normal is going this way. That means v dot n will be negative. Okay, so for any control surface, okay, the momentum is represented this way, right? So for this control surface at 1, I can write this as minus u1 rho u1 a1, okay, and so that's what is coming in, and also we have stuff going out here, but we are considering the linear momentum in the x direction. So the x component of this guy, if you look at it, is going this way, whereas the normal is outside, so or going in the same direction as this velocity here. However, we'll still end up with minus v2 cos 45, okay, rho v2 a2, okay, and I can write this guy equal to the sum of the external forces acting on the control volume. One would be this pressure, and you can multiply with a force. To get the force, you need to multiply with the cross-sectional area, okay, and then based on our convention, this force here, anchoring force in the x direction, will be negative. And even though this is an exposed atmosphere, you should probably still write the pressure force here. However, if you consider gauge, this guy is 0. Okay, so here we don't know u1 and v2. We don't have to worry about it because we can use the conservation of mass principle, saying that the flow rate at section 1 will be equal to section 2, which will be some q. Okay, so I can write u1 in terms of q over a1, okay, and v2 also as q over a2. Okay, and if you put in all of these, now you would see that q will be the only unknown. We have one equation, one unknown. So if we solve it, q should be 7.01 cubic feet per second. When you do this, make sure you convert this inches, square inches, into square feet, and then everything will be consistent. Okay, so this is the first part of the problem. Okay, the second part is pretty simple here. You're asked to determine FAY. So again, let's try to write this guy equal to the sum of the external forces acting now in the y direction. So the conservation of linear momentum in the y direction. So you can see that this is the velocity component for this guy going out of this section. So according to the convention, it's in the negative direction. So I'll end up with minus rho v2 square a2 sine 45. Okay, and then this guy is also negative, so minus a minus fay. Okay, so again we don't have to know v2. If you want, you can find it since we already know q, or you can just substitute v2 as q over a2 here. Then your only unknown is fay, and if you do the math here, you determine fay to be 674 pounds. Okay, so this was the part which we were asked to do in class, and you see that that's pretty straightforward once we actually determine this flow rate correctly. Okay, let's look at another problem. Water flows as two free jets from the T attached to the pipe shown. The exit speed is 15 meters per second at both these guys here. The viscous effects and gravity are negligible. Determine the x and y components of the force that the pipe exerts on this T. Okay, so as soon as I see that viscous effects are negligible, that would tell me that I can probably apply the Bernoulli equation. First, let's identify a control volume just like this attached to this pipe here. Okay, so this is my control volume. Let me name this as section 1, section 2, and section 3. Okay, or just to be consistent, the way I solved, I took this as section 1, this is section 2, and this as section 3. Again, just to make sure, this is section 2, this is section 3. Okay. Okay, so again, we can do this problem based on what we have been doing in the earlier example. We can write the conservation of linear momentum in the x direction. Let's try to do that. Okay, so if you look at section 1, the velocity is going this way, whereas the normal is this way. If I represent this as x, this is y, I can write this as that. And at section 2, which is this guy, the velocity is going out in the positive x direction and the normal is also outside, so everything will be positive. Okay, and there is no x component for this cross section here at 3, so this would be equal to the pressure here, which would be gauge times A1, and if I write this, guys, okay, it would be Fx and Fy, the reaction forces, right? So again, if I take that convention, it is positive plus Fx. Okay, so you see that in this equation, we don't know this guy, we don't know this, we don't know this. So we cannot really solve everything from one equation when we have more than one unknown. Okay, but however, you can find u1. The way you can do it is, you know that the way you set up the control volume, whatever is coming in should be equal to whatever is going out at these two outlets, right? So Q1 should be equal to Q2 plus Q3. Okay, the volumetric flow rates coming in should be equal to the sum of the volumetric flow rates going out. So A1 V1 equals A2 V2 plus A3 V3, right? And I've interchanged U1 and V1, that's fine. I can write U1 or V1, same thing, as long as you get the idea. Okay. You know A2, you know V2, you know A3, V3, you know A1. So if you put in the numbers, you'll determine U1 to be 12 meter per second. So now we know this guy, okay? And we already know this guy. But still we are ended. We still have two unknowns, so we have to try to figure out one of them and then we can solve for the other. Then we'll end up with one equation, one unknown. Okay? Since its viscous effects are negligible, we can apply the Bernoulli equation going from along a streamline going from 1 to 2. Okay? So if I do that, apply the Bernoulli equation going from 1 to 2, P1 gauge over rho plus V1 square over 2, gravity effects are negligible, equals P2 gauge over rho plus V2 square. This guy is 0, it's open to atmosphere. You can similarly deduce this by drawing a streamline between 1, 3. You'll still end up with the same answer because V2 and V3 are the same. So P1 gauge, if you put in the numbers and do this, you should end up with 40.5 kilonewton per meter square or kilopascals. So you see that in the previous equation, from all the different unknowns, we now ended up with only one unknown in this equation. We have also determined P1 gauge. So now we can solve it. So if you put in all the numbers here and solve it, you get Fx to be minus 72,000 newtons, and don't be worried about the negative sign, it just means that Fx, the way we represent it, it's acting in the opposite direction, so it is acting this way. Okay, and we are also asked to determine the y component, which should be straightforward. So now we can apply the conservation of linear momentum in the y direction. You see that there is only one cross section here where this y component of velocity, okay, which should be equal to this sum of the y forces, which is just Fy here. So rho v3 square a3, again v3 and the normal are in the same direction, so by now you should know why I can quickly write this will be equal to Fy. So from here I know v3, I know a3, I know rho. We should determine Fy to be 67,500 Newton per meter square or pascals, and this is, as we represented, is acting in the positive y direction. Okay, now let's look at another problem. So a nozzle is attached to a vertical pipe here and discharges water into the atmosphere as shown in this figure. When the discharge rate is 0.1 meter cubed per second, the gauge pressure at the flange here is 40 kilopascals. You're asked to determine the vertical component of the anchoring force required to hold the nozzle in place and the nozzle has a weight of 200 newtons, and the volume of water in the nozzle is 0.012 cubic meter. That means you probably have to consider the weight of the water as well. And you're asked to determine, is the anchoring force directed upward or downward. Okay, so let's represent your x and y directions here, and let me draw the control volume connected to where I'm interested in. Right, so this is my control volume. Let me name this as section 1, cross section 2. Okay, alright, so if I have that, I can do similar analysis I've been doing in the previous problems. So now we are interested in finding this anchoring force here, right? We should probably draw it to that point, which is some F A Y, right? So that's your anchoring force, and you know that there is this weight of the water, right? I'm going to represent it here just for clarity. So there is weight of the nozzle, and also there is weight of the water. Okay. Okay, so if we apply the linear conservation momentum equation in the y direction, okay, we can write that at section 1 is minus rho v1 square a1. Again, the normal is pointing outside, velocity is inside going in, so you'll have a negative sign. And then here you want to determine the y component of this flow field. Here your normal is pointing in the same direction as your velocity vector, so this would be a positive rho v2 square sine 30 a2 will be equal to sum of forces acting externally on this control volume. There is this pressure times cross sectional area, right, which is acting in the positive y direction, and there is this reaction force which is acting here minus, and if I represent it as downward, it would be minus ay. Okay, some reaction force here, and the weight of the nozzle minus the weight of the water. Okay, and I know weight of the nozzle. Weight of the water, I can write it as volume of water, okay, which is your given here, times the specific weight of water, which you can find from the tables. So that would give you the weight of water in this region. Okay, so if you look at in this equation, you don't know V1 and V2, but you know V2A2 will be V1A1, conservation of mass, will be equal to Q, which is 0.1 cubic meter per second. So you can represent V1 in terms of QA1 and V2 in terms of QA2. Okay, so those are known, and you know A2, you know PA1, you don't know this guy, you know this, right? So the only unknown here is FAY. Okay, so you'll determine that easily by putting in the numbers. So you would determine FAY to be 482 newtons. Okay, and since we ended up with a positive quantity, the original direction is right, so it is acting downward. Okay, so this problem, even though it's looks a lot of statements, all you had to do was identify the control surfaces, define a control volume, coordinate system, and apply the appropriate conservation of linear momentum in the direction you want based on what you're asked to find, and off you go. And the rest of it is just applying the conservation of mass, and you'll determine your reaction force. Okay, let's look at one last problem for the topics we covered till now. So air flows into atmosphere from a nozzle and strikes a vertical plate as shown in this figure. Okay. The horizontal force of 12 newtons is required to hold this plate in place. We're asked to determine the reading on the pressure gauge. Assume the flow to be incompressible and frictionless. Again, that should tell you that you can probably go ahead and use the Bernoulli principle here if needed. Okay, and it would so happen you might see that it would be needed in this case. Okay, so let me represent point here in the flow field as 1, point in the free stream as 2, and a point here as 3. Since we have done a problem like this, by now you know that this is the control volume you would pick, okay, for this region, and you know that the momentums in this direction, if you say x and y, cancel out each other since you assume that the flow is symmetric. Okay, first let's try to determine if we can write a relationship for pressure at 1. So since it's incompressible and frictionless, I can go ahead and apply the Bernoulli equation going from 1 to 2. I can neglect the elevation effects here since they are in the same z. So P1 gauge over rho plus V1 square over 2 equals P2 over rho plus V2 square over 2, and V2 is free stream, so it's P2 gauge, so this is 0, right? And you can immediately see that we don't know P1, we don't know V1, we really don't know V2, right? Whereas you know that whatever is air coming out is what is coming in to at section 2, right? So Q1 based on your conservation of mass, or A1 V1 equals A2 V2. Okay, so you can substitute this guy in here, so I would end up with P1 over rho plus A2 over A1, okay, V2 squared divided by 2, okay, equals V2 square over 2. Okay, so I have written everything in terms of one variable V2, because V1 is nothing but A2 over A1 V2, so that's why you have the square. Okay, now you end up with two unknowns. Maybe this is something we can work with, because you know that if this is your control volume, you have solved this problem in class, you can apply the conservation of linear momentum in the x direction here. So your velocity in the positive x, whereas your normal is pointing out, right? So again, if I apply that, I get minus V2 rho V2 A2 will be equal to negative 12 newtons force in the negative x direction based on the convention, right? So if you put in the numbers and density of air from the tables, you should determine V2 to be 57 meter per second. Okay, so now that you have that, You know V2, you know these guys, you know this, so you have an equation and only one unknown. Just make sure you put in all the numbers and check for units. You should end up with P1. Gauge is 1820 pascals or 1.82 kilopascals or 1.82 kilonewton per meter square. Okay, this concludes the session for the topics we covered till now in this chapter. Looking forward to talk to you again next time.